Good afternoon. Good afternoon, ladies and gentlemen. My name is Michal Vavrečka, and I will present for the first time in Prague our product called PRAG. So imagine that you are like a researcher, robotic researcher that has a lab with the robots, and the task is to create a general behavior in this robot. And you will soon realize that you spend like a 90% like creating the task evaluation, fine-tuning the rewards, and doing this for a new task is all the time the same. And you start to think how to create a general behavior, and you realize that you need the data. I mean, similar to large language models, you need the big data. But how to create such a big data? So we had the same problems, and that's why we created the PRAG. At the time of the paper submission, we had only the symbolic part of it. That's where it's called like action sequence symbolic generator. But I will show you also the later development dedicated to fully check it in a simulation. So, from a psychological perspective, you can imagine PRAG as a part of the human brain. I mean, if you are trying to develop new tasks, you can use some intrinsic motivation, or you can have some predefined stuff. But we came to the conclusion, so the best way, I mean, how to create a robotic brain and train the policy, these are the policies that you train in the environment, is to have something like a semantic knowledge. So it has the vocabulary of action, objects, and predicates you are interested in. So this is what you define as a user. And then there is a creativity phase. So the brain of the robot, but I mean it's a PRAG inside, is going to generate out of these atoms is going to generate the symbolically valid task. That means the robot is start to think, if I do have these atoms, what task I can create. And if he create task, I will show you later how, he start to imagine. So not only in symbols, not in high-level description, but also in a reality, whether the task is feasible. Because if I'm going to invent nonsensical task, then I can train on this task like forever. So the loop is about I'm going to create a task based on these constraints that will sequence basic actions, and that will create initial and goal states that is good for automatic evaluation, because you know what's the task progress, and it's going to work in a loop. So I'm creating the combination, I'm checking the feasibility, and then I'm training robot on this task. If I'm going into the detail, so how it works, I mean the symbolic part, it means you will define as a user set of actions. I will show you in the next slide what action we selected. Then you do have a predicate. Predicates are pretty, I mean, they are missing in your simulators. I mean, nowadays simulators always use, when you are spawning objects, you are spawning in a volume. But most of the task is about I'm putting something on something. I'm putting something left to something. So the predicates are very powerful, and they are powerful also for checking the task progression, because they can tell you, I mean, what's your progress. So having the set of a good predicates is I mean, the mandatory part for the automatic execution. And then you do have a set of objects. This is up to you. You do have a meshes, you do have labels, and all these set of objects are then used in a simulation. Then you will run the symbolic constructor or symbolic generator. The last part is you are also defining how long the sequences has to be. So you can start with the task like approach and grasp, but you can chain, I mean, up to do, let's say 15 atomic tasks together. And this symbolic generator is based on just the symbolic validation. So it will not tell you whether the task is feasible physically, but it will tell you whether the task is feasible symbolically. So all the predicates for initial and goal states are satisfied. So the task can be passed to this physical validation that will tell you then, okay, feasible task, let's start to train on it. Okay, what are the, I mean, what are atomic actions? We did some basic analysis and we came to the conclusion that if we do have just these 8 basic, we call it atomic actions, then we can solve any more difficult action or as a composition of a sequence of actions. So these are antagonists like approach, withdraw, grasp and drop, and there is a translational and rotational stuff based on moving and rotating based on following the trajectory. Yeah, and then everything else is just a combination of these. So these help, but I mean it's up to you. You can define your own proto actions. This is your vocabulary. So when you do have these, then the generator, then the symbolic generator is going to sequence them. So it's going to create initial and goal states, and it means also you have a task evaluation. Okay, so this is the basic description. I mean, the difference between all sequences that are that you can combinatorically create, and then there are these that are like a symbolically feasible. And you see, this is like a starting action, this is the length of sequence, so easily you can, if the sequence has let's say 15 proto-actions, you do have tens of millions of feasible tasks. So this is like a cheap generator of the training task. It's hard. I mean, at this symbolic part, we try somehow to measure the similarity between tasks, because all the combinations, I mean, you need to also have this semantic meaning for them. But we believe, I mean, at the end, I will tell you it's similar to Excellent 2 from a Google. I mean, if you train in all combination of the world, then the general behavior will emerge from this training agent, because he will be capable to solve also the task it was not trained on. So, but we measure some similarity between tasks in a symbolic space that is not continuous space is difficult. So these are some symbolic metrics, and then this is the part where if you do have this definition, I mean, every goal state of previous action is initial state of the next action. So this is basic pick and place task. So I need to approach, grasp, move, drop. So the generator will create me these, the description of the environment. And then in a simulation, I'm going to spawn it, and I'm going to check whether the task is feasible based on some inverse kinematics planner or just spawning the arm into that positions. So the task is considered valid. Then you can run the training loop, and now you can see, I mean, these are the basics. We are still fine-tuning this phase, and this is work in progress. So you train the robot. You see that the grasping is somehow, because the grasping itself in a simulation is very difficult because of the simplified physics. So we use grasping just when you close the gripper, it's going to be magnetized. And this is like a long task composed of several objects that you manipulate, and it was trained based on this method. Okay. The good point is that you can run this generator on any robot. So we tested on any embodiment. So you can take your robot, you can take your objects, you can take your the predicates you would like to learn, and then you can run the machinery. You can constrain, I mean, how long the sequence is going to be. This is all about the constraint. You don't need to define task. All you need is to define the constraint, how big is going to be the training space. And I think, yeah, it's all. So this is this tool. We are developing it, and we are trying to, I mean, at the end, we would like to create the general engine. So we will try to train the policies or our multi-policy algorithm that is capable to learn on this. And you have a huge amount of data, and all the robots we are training are somehow aligned with the real robots. So we are also, I mean, doing the sim to real transfer. And the core idea is similar. Again, I said it's like Xland. Xland was a toy environment with a simple agent that was capable, after playing like millions of trials, was capable to solve the semantically meaningful task. And this is like a robotic equivalent that works with the real environment, with the sim to real transfer, and has to offer the same capabilities. Okay, I think it's all. Thank you for your attention, and I'm ready for questions.
Thank you very much. So we have time for 2 or 3 questions. Do you have any question? Yeah.
Hi, thank you for your talk. This reminds me quite a bit of the CRAM cognitive architecture. Are you familiar with it? What's, in your opinion, that was missing in that you're adding with this contribution?
Okay, I'm not aware of this, so I can't compare it. I mean, directly. Okay.
Okay, because it seems quite similar, because they also have
so
symbolic and some symbolic. It might be quite interesting to see.
I will look at this, and then I can answer.
So yeah, go ahead. That's right.
Hello, what's the difference with PDDL? Because there's also a language in which you have predicates and actions and you make planning.
What's the difference between
PDDL with your approach and PDDL?
PDDL, I mean, this is similar, but in a PDDL you can generate the symbolic task, but this is let's say something on the top of it. I mean, the formalism behind this symbolic checker is very similar to PDDL, or in iGibson it's a BDDL, but there is an inspiration from this.
Okay.
Hi, quick question. The gripper you said is a very simple magnetic thing one. Since you have so many different robots that you are trying to have, like humanoids or just robot arms, are you also intending to update or change the grippers and make them more complex? Or
Yeah, this is. I mean, right now we are working on this. I mean, have a universal definition of this gripping mechanism. I mean, we were capable to train even with the real grasping, but it's like 40% of the errors is just because of the physics of contact points will create the error during training. So the robot is incapable to hold and move the object, especially in this moving manipulation task. I mean, it mostly holds some object, and these calculations are not, I mean, in the reality, the robot is capable to hold the object, but in a simulation, this is still like unsolved problem with the grasping. But yeah, we are working on this.
Okay, thank you. So if you have one more question, I can take. No? Okay, our time is almost up. So thank you very much.
Thanks.